if we're running a two-tailed hypothesis test. So when we do this, we would set a significance level. So let's say we're working with a 5% significance level. Then the image that we'd be working with is we'd have our bell-shaped curve that we're working with, and then that 5% would create this kind of rejection region in the tails. So in those two tails, I'd have this total of 5%. So it's like in one tail, I'd have 2.5%, and in the other tail, the other half of that, which means in the middle, I would have 95%. And this picture right here should look familiar from our work with confidence intervals, in that this was the setup for our 95% confidence. Well, with these two-tailed tests, the significance level and confidence level should always add up to 100%. So if we're doing a test with 5% significance with a two-tailed test, that would link to 95% confidence intervals. So there's this connection between confidence intervals and hypothesis tests to the point where we can use a confidence interval to make our conclusion for a two-tailed hypothesis test. So when you have a question dealing with a two-tailed hypothesis test, there's kind of two ways you can go about it. You can follow the steps that we went through previously, and I'll show that at the end of this video since we haven't really seen a two-tailed test yet, or you can use a confidence interval. So starting with the confidence interval, what we can do is build an interval around our sample proportion. So we grab our sample data, create this 95% confidence interval around it, assuming we're working with 5% significance. And then it's just a matter of if our proportion, so we will have a null and alternative hypothesis. And with our alternative hypothesis, it'll have to be that we're trying to prove that a number is different or changed. But the idea is if that proportion from our null hypothesis, if that is in the interval, then we failed to reject the null hypothesis. If that value is outside the interval, we reject the null hypothesis. So let's see how this works together in an example. So in 2008, the Centers for Disease Control and Prevention reported that 34% of adults in the United States are obese. A county health service planning a new awareness campaign polls a random sample of 750 adults living there. In this sample, 228 people were found to be obese based on their answers to a health questionnaire. Do these responses provide strong evidence that the 34% figure is not accurate? So, setting up just a null and alternative hypothesis here for the proportion in this county that are obese, we would assume it's the same as the rest of the United States, and we want to try to show that it's not accurate for this region, so we want to show that it is actually not 34%. But then what we have in here is some sample data. So we have this sample of 750, so 228 out of 750 was our sample proportion, which would be a 0.304. So what we really want to see is with this county that has 30.4% obesity rate, is that significantly different from 34%? So what we're going to do is build a confidence interval, a 95% confidence interval around our sample statistic. So as a review of our confidence intervals, first thing we need to do is check the central limit theorem. So we're going to check for independence, randomization, and success failure. So independence, randomization, sure. And then success failure, 750 times 0.304 should be that 228. And then 750 times 1 minus that value, which is a 0.696, should come out to be, typing into the calculator, should be a 522. Both definitely more than or equal to 10, so we're all good there. So then what we're going to do is construct the confidence interval. So we'll take our sample statistic, 0.304, plus or minus our z star, so 95% confidence always has z star of 1.96, square root 0.304 times 0.696 over our sample size of 750. So we'll have 0.304 plus or minus. If we plug in for a margin of error, it's a 0.0329. And then subtraction for our lower bound is 0.2711, upper bound 0.3369. So what we want to do now is compare. We won't go the next step of making our conclusion like we usually do. What we want to do now is run our two-tailed test. And to do that, all we need to really think about is our null hypothesis, or even our null and alternative hypotheses. So if we think about what we're trying to prove here, we're trying to prove that the population proportion is different from 34%. So what we could do is look at this interval and see, is that 34% in there? Is that a possible value for our population based on our 95% confidence interval? And you could also think of it in terms of the null hypothesis. We're saying the proportion is 34%. So it's similar to questions that we asked in the previous section with confidence intervals, as you find this interval, and then if I said, is 34% a likely outcome for this? Well, no, it's not, because 34% is outside the interval. So what we're looking at in this case is the second scenario where the value from our null hypothesis is outside the interval, so we would reject the null hypothesis. The idea being our null hypothesis can't be true here based on this 95% confidence interval. So what I would say here is that I'm going to reject the null hypothesis. And we won't have a p-value here, but you could say with 95% confidence, you could bring in the confidence. You could also say with 5% significance, that would be the same thing. And then we would say there is evidence that the 34% figure is not accurate for this region. So it came down to finding the confidence interval, and it's just a matter of whether or not that value from the null hypothesis is in the interval or not in the interval. In this case, it was outside, so we got to that conclusion of rejecting the null hypothesis. Then just to run through, since we haven't really done a two-tailed test, and just to kind of prove you'll get the same solution in the end, your hypothesis test, so it's a longer process typically for hypothesis tests. So this is where if you're doing a two-tailed test, if you're comfortable with those confidence intervals, that can be a good alternative. What we're going to do is we have the same null and alternative hypothesis. I'm going to check the conditions. Now the conditions here change a little bit because up above there we use our sample statistic. Sorry, getting a little carried away of talking and writing at the same time. Up above we used our sample statistic, but when you run the hypothesis test, when you take your sample size, you want to use the value from your null hypothesis. So here we actually want to multiply by 0.34 and 0.66. So let's see, that'll be 255. This will be 495. Both are larger than or equal to 10. So we're all good to go there. Then we'll go ahead and set up our mean and standard deviation. I'm going to put that in over here. So mean of 0.34, standard deviation, we'll take the square root of 0.34 times 0.66 over sample size of 750, which that should give us a standard deviation of 0.0173. And now it's time for the p-value. So this is the case of a two-tailed test. So we'll have 0.34 in the middle there, but what we want to end up with is these two tails. Now our sample statistic that we're plugging in there is the 0.304 from up above. So 0.304 or 30.4% is on this lower end. So what we're going to end up doing is in GeoGebra, we'll find this area to the left and double it, so that then that'll bring through this area that's also to the right-hand side. So for p-value, I'm going to take 2 times, and then the area to the left of that 0.304. So going to GeoGebra, centered at 0.34, standard deviation of 0.0173. And then we want area to the left of 0.304, which is a 0.0187. So that gives us the area to the left, and we want to double it. So if we multiply that by 2, we should get a 0.0374. And then we'll go ahead and compare that to 0.05 to see which is smaller. And we'll see our p-value is small. Which means we're going to reject the null, which means we have evidence for the alternative. So our conclusion here, we could switch it to stating the p-value, but for our conclusion, it's going to be the same as what we found up above there from our confidence interval. So with the two-tailed tests, you'll reach the same conclusion as long as you do them correctly, but you can use confidence intervals as an alternative to solving those hypothesis tests, only in the two-tailed cases.